September is the start of the school year for many students around the world, and we at SciShow have the luxury of learning all year long, but many young people are not in school simply because they can't afford it. That's why YouTube is partnering with Comic Relief to raise money for education. It's School of YouTube Week, where we can all learn something new so that others can too. A little goes a long way. $5 will pay for a child in Zambia to go to school for 2 months and have a meal there every day. If we can raise $500,000, we could help over 5,000 children go to school and have a meal there for a whole year. If you want to help, go to comicrelief.com and donate. Or if you're in the US, you can text SOYT12 to 71777. Message and data rates may apply. If you're in the UK, text SOYT12 to 70005. Texts cost £5 plus your standard network message charge. £5 per text will go to Comic Relief. You must be 16 years or older, and please ask the bill payer's permission. For full terms and conditions and more information, go to this link.
Hi, this is Hank from SciShow. This week on YouTube, it's the School of YouTube where YouTubers learn things. We're learning things all the time on SciShow, but I'm very excited right now to have Phil Plait, who is the Bad Astronomer of badastronomy.com. You've been talking about astronomy and science and advocating for science for a long time.
Since you were a fetus.
Wow. There are many things that I do not understand about the universe, but I think I'm going to go with something fairly simple that I've never been able to get my head around. How do we know how far away a star is? We're looking up there, and you can see some of them are different brightnesses, but that's really all I can tell. Like, and how can we say that's a brighter star because it's closer, that's a brighter star because it's bigger? This seems like an impossibility to me, from our one vantage point of the Earth, to have any idea how far away something so far away is.
Well, I'll ask you, how do you know how far away something is when it's right in front of you?
I could either get a tape measure,
okay, right,
which I can't do with a star.
That is, well,
I'm pretty sure that we don't have any tape
that would be
measures
hard.
that
it would be hard.
That are light years long. Or I use my 2 eyes, and so like I go like,
bingo.
Okay.
Right on the nose.
But we've only got one planet to look from.
Ah, but our planet moves. And that's how this works.
That's totally true.
The basic way this works, when you're looking at something and it's far away or medium distance, we have 2 eyes, and one eye sees it at this angle and one eye sees it at this angle. And our brain processes those 2 different angles and can figure out how far away an object is. The farther away it is, the more parallel our vision is, and the closer something else is, the harder we have to cross our eyes to see it because the angle is much, much wider. We can do that with the Earth as well. Stars are very far away, and our eyes are too close together to be able to see that angle. At basically past a few meters away, everything just looks the same distance. But the Earth is going around the sun. And so the Earth takes a year to circle the sun once. And so at some point it's here, and 6 months later it's over here. And that makes a binocular angle just like our eyes. And it turns out the closest stars are at a distance where, using telescopes, measuring their positions day after day for months or years, we can actually see the stars moving back and forth as the Earth's moving around the sun. And this process is called Trigonometric Parallax because you're using trigonometry, and parallax is just the idea of measuring a distance to something. And that's how we did the nearest stars.
But there's a certain point at which stars are so far away that it basically looks the same to our telescopes.
Yes. Now, if you use a bigger telescope or put one out in space where our atmosphere isn't making the image swim and dance, you can do a little bit better. And you can actually see out to a distance of about 1,000 light years. And there are a lot of stars out to 1,000 light years, so we can do this pretty well. But past there, yeah, the Earth's orbit isn't big enough, we can't do it. But we have another technique where you can say, oh, here's a star that is 200 light years away, we've measured its position very well, and we see a star exactly like it, but is 100 times fainter. Well, if it's 100 times fainter, it must be 10 times farther away, because the more distant something is, the fainter it is, and it goes with the square of the distance. So if something is 100 times fainter, it must be 10 times farther away. And you can measure the distance of this other star by bootstrapping it from the one you know.
But we have to know a lot about the kinds of stars there are out there in order to do that.
And we do. We actually have been doing this for a long time, more than a century. And we can look at 2 stars and compare them For example, taking their color or taking their spectrum. Look at each one, break their light up into thousands of colors, and that pattern of light, there are chemicals in the atmosphere of a star that absorb certain colors of light. And so when you map that out, you get a graph that has bumps and wiggles in it. It's a bit like a fingerprint. Yeah. And so you can say, oh, this star is cooler than this one, or this one's hotter, or this one's more massive. You can do all that. And you can say, oh, this star looks just like this one, but it's dimmer, must be farther away. And you can generate a distance to that more distant star.
So is there like a special parallax term for that thing as well?
In fact, yes. And basically they are more bootstrapping extrapolations. Now we know that if we see that kind of star that we've already measured the position of, that it's close by, and we're seeing it farther away at a different star, we can figure out how far away that is, and you can work your way out to the galaxy that way. But it turns out there are other galaxies where we don't necessarily see individual stars in them. And there are other methods of finding out how far away those galaxies are, how fast they're moving away from us, if a star blows up in them, lots of things they can do to let us know how far away they are. And we call this basically the cosmic distance ladder. Each rung is built on the rung before it. And by doing this, we've gone from measuring the distances from the moon and the sun out to the stars and the galaxies and distant objects in the universe itself.
I hadn't even thought about how we would measure how far away a galaxy is. That's a different question. And
it's related.
No, it's totally, but like, wow. It's just that, it's not that I just didn't expect to get there, nor did I even consider how amazing it is that we know how far away other galaxies are.
That's something that was done by Edwin Hubble and other people back in the 1910s and 1920s. They built telescopes big enough to see stars in other galaxies and measure their distance. And then they discovered that galaxies are moving away from us, and that how quickly they're moving away depends on their distance. And again, that's the next rung, and you can bootstrap that all the way out to literally seeing the expansion of the universe itself. And even the fact that the expansion is accelerating. And we discovered this in 1998. 2 different teams of astronomers looked at the universe, found out, hey, it's getting bigger more every day. It's getting bigger faster now than it was yesterday. And that was because we had measured the distances to these very, very distant objects in the universe.
What must it have been like for Edwin Hubble to realize that even as many stars there are in our galaxy, that there are other galaxies out there? Like, how much of a mind shift? Like, how, like, that's so, like, philosophically significant.
Yeah.
And then, like, to like, then be the person who just, like, has to tell the whole world about that.
It was a change in the paradigm of astronomy as much as discovering cells were for biology or something like that. There was a big argument. You know, we go out with our telescopes, we look up in the sky, we see these fuzzy objects, we're going to call them nebulae, which means gas clouds. And some of these things are forming stars, and some of them are spiral-shaped and fuzzy and weird-shaped. And there was a big argument, a big debate, literally a debate, in fact. Were these objects in our galaxy, or were these distant galaxies themselves? And it was in the 1920s that was resolved. And these are, yes, separate objects. Our galaxy is not the universe. Once again, like we've done over and over again, astronomy is good at this, shook its finger at us and said, you guys got too big of an ego on you. You're a lot dinkier than you thought. And no, the Milky Way isn't the whole universe. It's just one galaxy. And it turns out there are hundreds of billions of galaxies just like it in the universe.
And we've only known that for less than 100 years. We learn fast.
Yeah, and there's a lot more to figure out.
I found this personally extremely fascinating. This was a very brief conversation, and I hope that we will continue it over drinks later tonight.
Absolutely.
But you, unfortunately, won't be there for that. But thank you for everyone for checking out the School of YouTube this week on YouTube, and for helping out and donating for comic relief, because we can learn things and have a good time and make the world better for everybody all at once, which is pretty amazing. Thanks to YouTube for doing this. Thanks for Phil for coming on SciShow.
Thank you.
A pleasure.